Jai to all. Today I am here to present the fourth video lecture of the subject Control System BEC 602, and I am Dr. Amit Garg, Associate Professor in EC Department of AKGEC, and today's topic of lecture is signal flow graphs. Okay, so signal flow graphs are basically the representation of a system, simpler representation of the system by the branches and nodes, and by drawing signal flow graph of a system, we can easily find out the overall transfer function of that given system. These type of systems, basically signal flow graphs are applied for linear systems. Okay, so let us start with this signal flow graph concept. So the diagrammatic or pictorial representation of a set of simultaneous linear algebraic equations of a more complicated system is known as a signal flow graph. Okay, and SFG applies to linear systems and presents the flow of the signal in the system. Okay, so by seeing a signal flow graph, we can easily see that in which particular direction signal is basically traveling. It is important to note that the flow of the signals in SFG is only in one direction. So it is important to note that between two nodes, signal direction will become unidirectional. Okay. The transfer function of the system, which is represented by SFG, can be obtained by using Mason's gain formula. Okay, so Mason's gain formula is basically, you can say, by which you will find out the overall transfer function of the given system, or in case of signal flow graph, we can also call it overall transmittance of the system. It is important to note that we can also find out the overall transfer function without using Mason's gain formula. But that method will become very complicated when the number of variables are large. Means if the number of nodes and number of branches are higher, in that case, if we want to solve it overall, if you want to find overall transfer function, then it will be a bit complicated to solve that without using Mason's gain formula, because in that case we have to make the simultaneously linear algebraic equations, and let us suppose if we are having if we are having 7 equations, so it is very difficult to solve the solution of those equations. So that's why Mason's gain formula concept in existence, by which we can easily find out the overall transmittance of the given system without solving linear equations, but simply so this how Mason's gain formula works. So in case of Mason's gain formula, we can find out the overall transmittance simply by checking that how many forward paths are there in the system, how many loops are there in the system, and non-touching loops and this. So we will find out those forward paths and loops and other things, and based on that Mason's gain formula, then we can find out the overall transmittance. So the dependent and independent variables in the set of algebra equations are represented by nodes in the SFG. So nodes is basically defined like this. The branches are used to connect different nodes present in the SFG. The connection between the different nodes is based on the relationship given in the algebraic equations. Okay, so between two nodes, so branches are basically used to connect two nodes, and each branch is having some transmittance value. Okay, this is nothing but the transfer. This is nothing but, you can say, if you will compare it with the block diagram, so that is nothing but the transfer function of that block. So transmittance is written over the branch. Okay, so now come to the SFG terminologies. Okay, so there are various terminologies which we require to understand to find out the transmittance using Mason's gain formula. First of all, input node. So an input node is a node that has only outgoing branches. Okay, output node. An output node is a node that has only incoming branches. Path. A path is any collection of continuous succession of branches traverse in the same direction. Okay, and the forward path. A forward path is a path that starts at an input node and ends at an output node. Path gain. The product of branch gains encountered in traversing a path is called the path gain. Forward path gain is the path gain of forward path. Loop. A loop is a path that originates and terminates at a same point, same node, and it is important to note that no other node should be encountered more than once. Okay, and loop gain is the path gain of a loop. Non-touching loops. Two parts of an SFG are non-touching if they do not share a common node. And self loop, the path that starts from one node and ends at the same node without traversing any other node is as the self loop. Means the starting and terminating node is basically the same and there is no other node involved in the process. Okay. So this we can understand all these things using this signal flow graph. So you can see, if you will see this particular path from RS to CS in this direction, this is basically nothing but a forward path. Okay, because this path connects the input to the output, and the gain of this forward path is the forward path gain, which is equal to the multiplication of the transmittances of the branches. It means this, if you'll write the transfer function of this forward path, if we'll write the forward path gain, then it will become G1, G2, G3, G4, G5, G6, G7. So this is your forward path. And if you will see loop, so this is nothing but a loop because the starting and terminating point is the same. This is also a loop. This is also a loop. Okay, you can see here, this is also a loop. Okay. So these are the loops because the starting and terminating point is the same. So loop gain is basically the multiplication of gains. It means G2 into minus H1. So minus G2 H1 is basically the gain of this particular loop. Okay. So these are basically loops. Maybe some other loops will be involved here. Okay. This is self loop. Self loop, you can see only this node is involved here, and basically it is the starting and terminating point and no other node coming over here. So this is basically the self loop. Okay. And if you will see the pair of non-touching loops, if you will see this particular and this particular loops are non-touching, pair of non-touching loops. Okay. So if you will make these are two loops which will make a pair and they are not touching with each other. That's why it is called pair of non-touching loops. So why we are, and this is your input node, you can see there is only outgoing branches. This is your output node, you can see only the incoming branches are there. Okay. So basically, this is basically the terminology which we have seen. Now, based on this, we can easily find out the transmittance. How? First of all, we will see the Mason's gain formula. So you can see Mason's gain formula is Pk summation k equals to 1 to k Pk delta k upon delta. So Pk is basically forward path, number of gains of forward paths. So first of all, we have to identify that how many forward paths are there in a particular signal flow graph and what are their transmittances values, or what are their what are their path gain basically. Okay. So Pk is this, delta k is basically you can say is the path factor. Okay, associated with the concerned path. Okay, means if we are talking about path 1, if we are seeing about path 1, so we have to check that if there is any loop which is not connecting with this forward path. If this is not connected with the forward path, then this is equal to if it is connected to that forward path, then it is 1. Otherwise, 1 minus loop gain of path not touching with that forward path. Okay. So it means if there are 5 paths, it means there will be 5 values of path factor, delta 1, delta 2, delta 3, delta 4, delta 5, and delta. Delta is basically, you can say it is the graph determinant, and its formula is like 1 minus sum of all individual loop transmittances plus sum of loop transmittances product of all possible pairs of non-touching loops minus sum of loop transmittance products of all possible triplets of non-touching loops, like this. Okay, so by using this particular formula, we can solve any problem of signal flow graph using Mason's gain formula. Okay, so here for this particular question, we will see that how we will find out the overall transfer function of the given system. Okay, so you can see the signal flow graph is directly given to us. Okay, So now first of all we will identify that how many forward paths are there in the system. So these are the forward path. This forward path 1 you can see here, and forward path 2 you can see it is like this is your forward path 2. Okay, and these are the corresponding path gains G1, G2, G3, 4, G1, G4, G5, 8. You can see G1, G2, G3, G4 in first case. In second case, G1, G5, path gain is G8 and it is G4. So G1, G4, G5, G8. Okay, and so these are the only two forward paths. Now we will see how many loops are present. Okay, so you can see one loop is this G1, G2, H1 means this is one loop, this is another loop. Okay, so this is another loop. Transmittance is first one is G1, G2, H1, second one is G3 into G4, and third one is this is basically also a loop. Okay, so transmittance is G5, G6, so this is 1, 2, 3, and fourth one is bit complicated to identify, but it is still there. You can see it is from it is like okay, and you can see the transmittance in this direction, and then it will come like this. Okay, so this is basically the fourth loop, and fifth loop is basically the self loop. You can see the transmittance is G7. Okay, now we will see the combination of two non-touching loops. So you can see this first one and this one is non-touching. Okay, so the overall transmittance of this is G1, G2, G7, H1, and similarly if you will see the second one and also this one again non-touching, so this will become G3, G4 into G5, G6. Okay, and third one again this one is connected with this which loop, with this loop. Okay, this one is this one is making one pair with this and this, another one this and this. This one is making only one pair of two non-touching loop, this and this. So this is how we have obtained the path gains of all the loops, single loop or all the loops, non-touching loops, combination of two non-touching loops, and there is no pair of three non-touching loops. Okay, and now we can see we are having basically the two forward paths only. We are having two forward paths. So delta 1 is 1 minus, delta 2 is 1 minus. We will check if any other loop which is not touching the forward path 1. Okay, if there is any loop which is not touching the forward path 1, we will subtract the so this from this you can see this is basically you can see in our case it is delta 2 which is 1 minus G7. Okay, and if you will see all other routes, all other are touching with this forward path 1. Okay, so P1 delta 1 and P2 delta 2. Okay, and then basically so now we will multiply. So P1 delta 1, so P1 is G1, G2, H1. Okay, so what is the overall transmittance? P1 delta 1 plus P2 delta 2 upon delta, where delta is 1 minus sum of all individual loops. How many loops are there? There are 5 loops, so it means L1 plus L2 plus L3 plus L4 plus L5 plus sum of transmittance values of, so there are 3, so L21 plus L22 plus L23 like this. Okay, so this is basically the now you will put the value of delta over here, and delta 1, delta 2 we have already discussed. So when you will solve it, you will find the value of transmittance or overall transfer function is this. So this is a bit complicated system, okay, in which lots of loops and you can say number of loops are higher, and also there are non-touching loops are present in the system. But if problem will become simpler if the number of non-touching loops will be smaller, or you can say number of loops will be smaller, or less number of loops will be there. Okay, and this is how we will solve if the block diagram is given to us, and we have to find out the transfer function using signal flow graph approach. Another approach is block diagram reduction method. So in case of block diagram reduction method, we can directly reduce the block diagram, but here it is mentioned that you have to find out the Mason's transfer function using Mason's gain formula. Okay, so Mason's gain formula can only be applied over the signal flow graph. So for what we have to do, we have to first convert this block diagram into signal flow graph. Okay, so how we will convert it? First of all, we will identify the nodes, like this is one node, this is another node, and this is third node. Okay, now why we have chosen this second and third node? Because if any takeoff point, this is basically takeoff point, this is summing point. If takeoff point is coming just before summing point, then those two nodes are taking as separate nodes, and the transmittance between that line is basically the 1. Okay, and if the situation is vice versa, then you can make those as a single node. Okay, and this is your fourth node. Okay, and this is your fifth node, and sixth node is not required. Why it is not required? Because you can see here takeoff point is coming just after summing point, but here we have to take the node because it is coming before the summing point. So basically these are the these are the nodes. So 1, 2, and this is 3, and this is basically 4, and this is basically 5. So these are our nodes, and so we will replace these summing points and takeoff points by the nodes, and basically the transmittance in between them, basically the blocks that are connected between them will be represented by the branches of the transmittance value equal to the gain of the block. Okay, so you can see here G1 1, G2 1, and here you can see it is important to note that while in case of feedback, or we have to importantly see the sign of these summing points. Okay, because this sign will directly came into the transmittance value here, like this is positive, so it is positive, this is positive, so it is also positive. From here you can see minus sign is there, so that's why this minus sign will come with the gain value. Okay, and also here you can see it is H1, it is minus H1, so this is like this. Okay, so now we are having 5 nodes. Now we will see that how many forward paths, loops, and other things are there. So we can see only there are 2 paths, G1, G2 and G1, G3. So you can see this is G1, G2, G1, G3. There are 2 paths, and there are 3 loops. L1 is minus G2, H2. Okay, this is minus G2, H2. Another one is G1, G2 minus H1, and third one is G1, G3, G1, G3 minus H2. This if you will see G1, G3 minus H2, G2 and minus H1. So this is bit complicated to identify. So these are the transmittance values. Now we can see there is no non-touching loop, because delta 1 and delta 2 values are 1 because all the paths, all the loops are touching to both the forward paths. Okay, now we will calculate the determinant which is 1 minus sum of all individual loops. So L1 plus L2 plus L3. So when we will solve it, this is 1 plus G2 H2 plus G2 H1 minus G1 G2 G3 H1 H2. Now again the formula P1 into delta 1, which is G1 G2, plus P2 into delta 2, which is G2 G1 G3, and 1 minus sum. So sum will become this. So delta will become this. So this is the overall transfer function for the given system. So in this particular question, we have seen that how we will convert the block diagram into signal flow graph first, while before applying the Mason's gain formula. Okay. This is the signal flow graph concept, and we have easily solved basically the transfer functions by identifying the paths and the loops and their corresponding gains. So these are the references that I have used to prepare, use for making this presentation.